In 1993, Doom was released, and it was a breakthrough in gaming. It popularized 2.5-dimensional graphics, it had addictive and immersive gameplay, and it was also a technical achievement, pushing the boundaries of personal computers at the time. So traditionally, video games have been written by humans writing code. But 3 decades later, what we're seeing are things like text-to-text generation, text-to-image generation, and text-to-video generation. What we're looking at now is potentially a future in which we have text-to-video game generation as well. Today's paper is titled Diffusion Models are Real-Time Game Engines and comes from Google Research and Google DeepMind with affiliations with Tel Aviv University. Link in the description below. In this paper, the authors trained a computer model which is able to simulate an interactive version of Doom in real time. So in this video, I'll go over my understanding of how they did it, explain how diffusion models work, how they made it real time, and discuss some implications for what this might mean for game development in the future. Let's say that you're an artist and we're sitting in your art studio. In front of us is a blank white canvas, and I ask you, can you please paint a picture of a cat driving a red car? How would you go about this? A couple of questions might come across your mind. For instance, what kind of cat is in this image? What kind of car is in this image? What kind of scenery is in the background, and what's the composition of the image? Is the AI doing the same thing? How do AI models generate images in the first place? Well, a common technique used today is called denoising diffusion. So first, it starts with training data. Let's say for our example, you give your AI model 1 million pictures of cats and 1 million pictures of cars. Different types of cats, different viewpoints, different types of cars, different viewpoints. All sorts of angles. So now you have 2 million photos, and let's say you add some noise to all your photos. So now you have clear pictures of the cats and clear pictures of the cars, and also noisy pictures of the cats and noisy pictures of the cars. And then you add even more noise to it. So you have clear pictures of the cats, noisy pictures of the cats, and really, really noisy pictures of the cats, and the same for cars. Now's the fun part. Since you have all these images in your training data set and the model is able to recognize what all these looks like, you can now do something called denoising. So instead of a blank canvas, an AI model, if using this approach, actually starts with this. Just a big block of noise. So what you're doing, instead of saying paint this picture of a car and a cat driving it, what you're saying instead is, here is an image of noise. I know you've seen noisy images of cats and cars before. Can you please remove a tiny bit of that noise? By the way, this photo is a picture of a cat driving a car. Do you see it? And then the model says, okay, let me give it a shot. And it generates you something like this. And you're like, great, that's terrific. Let's do that again. So by the way, you know what noisy cats and cars look like. Here is what you have so far. By the way, this is a picture of a cat driving a car. Can you remove some of the noise from this image? And it says, sure. Let's do it again. And like, great, let's keep doing that. Let's remove more noise from this photo. And by the way, once again, this is a photo of a cat driving a car. All right, lots more steps. And then you get something like this. And then that's perfect. Just keep doing this, many, many steps of removing noise, and then you end up with something like this. So now, instead of pictures of cats and cars, let's say you want to simulate Doom. Well, you're going to need lots of training data from Doom. So what the authors did was they fed in a training set, rather they first created a massive, massive training data set of game footage of Doom with controller inputs. So in this case, they used open source VizDoom to generate 900 million frames of Doom along with the controller inputs. How much data is this? Well, at an assumed 35 frames per second, 900 million frames is 298 straight days of game footage. So how did they get 298 days of game footage? Did they scrape Twitch? Did they tie folks to controllers and force them to play Doom day in, day out? No. So what they did was actually created a separate model using reinforcement learning techniques and created a agent that can play Doom on their behalf, and then they just recorded it playing and its controller inputs. Check out the paper if you're interested in the data collection and the reinforcement learning to create the dataset. For now, I'm just going to focus specifically on how they simulated Doom using this data. So how was all this Doom footage used to actually simulate Doom? So, well, the authors started with an open source diffusion model, Stable Diffusion 1.4 specifically, and then they tweaked it essentially. It's basically saying, hey, here's a model, here's all the parameters in this AI brain. Let's adjust them all. Let's feed in this 900 million frame data set and let that adjust the AI model so that it's able to generate images of Doom. Now that you have a model that is able to generate images of Doom, you're going to be using it for something called next frame prediction. So let's just say you give your model the last 3.2 seconds of data, as well as the controller inputs that led up to it. And then you say, what's the next frame going to be? So in order to get this to be real time, however, you're going to have to generate this image really, really quickly. So if you used a lot of the AI image generation tools available today, you'll note that it takes a long time to generate one single image. But one of the reasons for that is because you want to generate a really nice looking end image. So you go through a lot of those denoising steps that we mentioned earlier. So for instance, in the cat driving a car example, we used over 25. In this paper, what they're doing instead, in order to generate those frames really, really quickly, they're only doing 4 denoising steps. So here's 3 seconds of data, here's controller inputs, here's what the player just pushed on the controller. What is the next frame? Answer it, generate it really quick. You don't need to go through a lot of denoising steps, just do 4. It's going to be very similar to the latest frame probably, and just do that repeatedly. With a number of tweaks, such as having a low number of denoising steps, the authors were able to achieve 20 frames per second. So the image generation happening 20 times per second, listening to controller inputs, resulting in a playable simulation of Doom generated on the fly. So how does the model remember information about the game state? Well, unlike a traditional video game engine, it's not tracking these values numerically. Rather, what it's doing is it's learning how to generate a logical progression of frames that adhere to the game mechanics based on what it's learned from the training data. It also doesn't hurt that there are a lot of visual cues in Doom in general that aid in it creating a consistent experience. So for instance, in the Doom UI, there are displays that show you your ammo and your health, for instance. So since that's available in previous frames, the model is able to leverage that to either increment or decrement those values based on the actions taken by the player. So what are some implications for the future now that we have a proof of concept of a neural model that's able to simulate and generate a game engine on the fly? Well, a number of things. For example, if you have a robust enough model, you may be able to generate new levels or make changes on the fly while you're playing, for instance. As an example, say you're playing a level of Doom and you just want to change, hey, there's a new weapon that looks like the crowbar in Half-Life. All of a sudden your weapon turns into that, for instance, or it's now available for selection. Another one, say this level has lava falling from the sky. The model knows what lava looks like and knows what things falling from the sky looks like. It can add that into the game frames as you're playing. Or you can make other changes such as, hey, this level, instead of Batman as my playable character, let's change it to the Joker. Maybe you can change your player, for instance. Or you can change enemies for that type of game. So for instance, instead of a giant demon as the boss, let's make it a ginormous spider instead. Right, that's it for this video. Thanks for watching. Thanks to the authors for a remarkable and nostalgic paper. Let me know in the comments what you think about this paper or where you think the future is heading. And like and subscribe if you want to help me keep cooking. Look forward to the next video. I'll be going over this bad boy right here. So it's not just artists and programmers, but AI scientists as well. All right? Cheers.